So hi everybody, my name is Manish and do you have right. So hi everybody, my name is Manish and this work I did with Nirmal and Pratik. So the topic of the talk is breaking into the window of primordial black hole dark matter with X-ray microlensing. So what I mean by these words, it will be clear as we go along. Right. So before getting into the nitty-gritties of what I mean by X-ray microlensing and what I mean by primordial black hole dark matter, we can ask a very basic question, what are the ingredients of our universe? So what CMB observation tell us about the universe we live in is that most of the chunk of the universe is so-called dark energy and dark matter, and only 4.9% is ordinary matter. So basically dark matter comprises about 85% of the total matter in the universe, and now I'll focus on what I mean by this matter. So before getting into dark matter, I'll just motivate. So this particular figure shows the map of recent literature about dark matter. It is taken from Inspire database. So you can see that there is a huge interest among people, but the dark matter problem remains unsolved. You can see these different archive bulletins. So people from different fields are interested in knowing what dark matter could be. So now, how do we know that this kind of matter should exist in first place? So we have various evidences for the dark matter in the universe. As you can see that from dark matter not only exists in small scales but also in large scales. So you can see in small scales we have flat rotation curve of galaxies, which is this particular figure. So ideally the velocity of this matter should fall as 1 over r, 1 over square root of r, but we observe flat rotation curve, which tells you there is some hidden matter there. And you can see there is a bullet cluster observation which tells you about how dark matter interacts. It mainly interacts collisionlessly because you can see that these gas clouds they have passed through, and due to friction they have slowed down because this is mainly baryons. And you can see most of the mass is concentrated in these particular peaks where we can't see any matter. So this tells you about the hints of dark matter. If you go to even large scales, you can see that we have this matter power spectrum, which tells you the presence of dark matter because we also observe structure formation. And if you go to even cosmological scales, we have CMB. And if you plot the 2-point correlation function and fit it to the lambda CDM model, and if you feed in the dark matter, you can basically explain the observation. These peaks basically describes the presence of dark matter. So I have motivated enough that dark matter exists. So now we can ask the question, what dark matter could be after all? So like from my previous slide, we already know that dark matter should be cold because meaning that it has to be non-relativistic because we observe the structure formation in the universe, and it should be collisionless, like the observation of bullet cluster that tells you that dark matter just passed through. It doesn't, unlike baryons, it just passed through, so it behaves collisionlessly. And it has to be a stable particle because we are seeing the effect now. And is it a mysterious particle? Hopefully in future it may not. So broadly speaking, we can characterize, we can basically categorize dark matter into two broad categories. It could behave like a wave or a particle, or it could be even a microscopic object like a primordial black hole, which this talk is focused on. And if it is a particle, we don't know its mass, charge or spin, whether it is a fermionic particle or a bosonic particle, we don't know about it. If you ask me about the mass of dark matter particle, that's where the situation is slightly embarrassing. There is a 90 orders of magnitude wide parameter space for dark matter mass. As you can see this particular figure, that ranges from 10 to the power minus 22 electron volt. So this dark matter behaves like a wave, and we have ultra heavy dark matter like primordial black holes. Now I'll focus on primordial black hole from now on. Right. So this particular figure shows you the primordial black hole parameter space. So the y-axis is the fraction of primordial black hole as compared to the total dm density, and x-axis is the mass of primordial black hole in solar mass. If you are not aware about solar mass, you can read the scale in grams from the above axis, and you can see that most of the parameter space has been constrained using consideration like Hawking evaporation, microlensing, and some other considerations. So basically, if you ask me about how do we form primordial black hole in first place, so basically we have mechanism for forming primordial black holes, like ultra slow roll inflation can give rise to some density fluctuations, and these density fluctuations can collapse into black holes during the radiation domination, and they can give rise to primordial black holes. And so the story goes back to 1974 when Hawking proposed that these primordial black holes could exist, and still there is a 5 orders of magnitude mass window. There is no constraint at all, and that's where I'll focus on. Here parameter space allows that the primordial black hole can contribute to dark matter 100%. So how do we basically gonna probe this window? So we can ask, can we ever probe this particular mass window? So the answer turns out to be maybe yes in future. That's where our work comes in. So what we saw is that using X-ray telescopes like NICE or STROBE-X and some future telescope XMU, we can hopefully try to probe these tiny PBHs if they exist. Okay. And now I'll describe about the physics involved after this particular slide. So you can see that so this is the big, slightly zoomed version of this particular thing, and this plot will come later as I'll describe the physics. So what are we talking about? So basically the mass and the length scale all involved in our problem is following. So like this window ranges from 10 to the power minus 16 to 10 to the minus 11 solar mass, and the Schwarzschild radius, if you convert this mass to Schwarzschild radius, this length scale turns out to be subatomic. It is good to have a visualization, that's why I have made this figure. You can see that this particular ball here is a primordial black hole of mass 10 to the power minus 12 solar mass, and this is the wavelength of a visible photon, that is 700 nanometer, that is shown to be 100 times smaller. So it is clear from this figure is that primordial black hole is much smaller than the wavelength of optical light. So these optical light, you can't expect to microlens these primordial black hole with the help of optical stars or something. So you have to do something else. So now if you go to even smaller mass, the 10 to the power minus 16 solar mass black hole is even smaller than hydrogen atom. So what we can do is we can go to higher energies so that the wavelength of light becomes comparable to the length scale of these PBHs. So that's why X-ray comes in. So that's why we are using X-ray pulsar to probe these tiny PBHs. And now I'll explain what I mean by microlensing. So what I mean by gravitational microlensing is that, so this cartoon figure simplifies it. So if there is a photon source, and photons are coming out of this source, and here happens to be a gravitating body. So from Einstein's theory of general relativity, we know that gravitating mass bends light, the photon get deflected, and so what you can do, it produces multiple images. So if as an observer one can see that it produces multiple images, if the mass involved is small, the separation between images would be small enough. It is typically of the order of micro arc second. That's where the name comes in, microlensing. So you typically can't resolve these images, and depending on the mass it could be even smaller, and the net effect you see is the enhancement in the flux of the source. So that simply comes from the consideration like Liouville's theorem. So so the second figure shows you the movie here. So you can see that there is a peak in the brightness when they are happens to be perfectly aligned, and the deflection is directly proportional to the mass of primordial black hole and inversely proportional to the impact parameter. And using this formula you can calculate what is the magnification, where y is the sort of, you can think of like a dimensionless impact parameter. And this is the lens equation if you consider geometric optics things. But here for our system, what I have told you till now, that basically breaks down because the scale, the length scale of these PBH is sort of comparable to the wavelength of light. So all of this breaks down. So you have to go to the wave regime microlensing. So you can define a W parameter, which is I call a dimensionless frequency parameter. It basically compares the sort of length scale of the primordial black hole to the wavelength of the light. So this is the lensing sort of, you can think of like time delay due to lensing, and this E gamma by h bar is basically the angular frequency of the photon. So Pictorially speaking, you can, if the primordial black hole size is smaller than the wavelength of light, you are essentially in wave regime. And mathematically, you can represent this situation by this condition. And if this is not the case, you are in geometric optics regime where your length equation is good enough. So here, for our system, we are here. So for this, the theory of gravitational microlensing, the magnification is given by this particular formula. And if you are interested, how do we get this formula, you can catch up after the talk. So here, this 1f1 is a confluent hypergeometric function that is basically taking care of all the wave effects in the problem. And this is the finite extent of the source. I'll explain in a while, after a while. And this is the pulsar property. We are using X-ray pulsar because we are interested in X-ray photon to microlens and detect the signature of this PBH that happens on the way. And this is the detector property, because detector doesn't, as a function of energy, detector behaves differently because detector's efficiency is depends on what energy we are detecting. And this AS basically is the dimensionless source size. So it turns out that the source is, because the primordial black hole size is as that of hydrogen atom, and here the source size becomes important because the Einstein radius of the lens is sort of comparable to the source size. So you need to take care of that. And what I mean by this FSE, finite source effect, is instead of a single point, we have a collection of points. So you have to basically take care of model source as a Gaussian profile, and what you will get, the net effect is basically what you get is the saturation in the magnification. It basically suppresses the magnification. That's why the signal is so faint. That's why this particular window is so hard to sort of probe. And the Einstein radius is given by this particular formula. It goes as square root of m, and depends on how far is the source, and x is the differential distance to the source. And one thing that I want you to remember is that this formula tells you that the magnification is frequency dependent. In usual scenario, magnification in gravitational lensing or microlensing is not frequency dependent. Here it is frequency dependent. So depending on frequency, we will see different interference patterns. If time permits, I'll show you those interference plots. So the idea here is that, so first proposed by these guys. So you have X-ray pulsars and you have a primordial black hole, and X-ray photons are coming towards the detector. This is nicer telescope on board on International Space Station. So these photons are coming. So here I have drawn line. Don't take it literally, because here we can't draw these lines because it is in wave optics regime. So what happens is these photons will get microlens, and the X-ray detector would be able to detect the presence of if some primordial black hole is along the line of sight. So here are some detectors that we consider in our work that is nicer, and a future telescope Astrobex that was expected to be launched on 2031, but now NASA didn't pass it. But yeah, let's hope for such telescope in the future. And we propose our own detector as well, that we call XMU, that stands for X-ray, a detector for X-ray microlensing. So what this detector is following. So you have this Astrobex effective area here. What we use is we use high energy detectors which is sort of behaves like Daksha, and you just scale the effective area by 2 orders. You just double the effective area. And here are some X-ray pulsars that we are using. These are the X-ray sources. These are the sources which are giving X-ray photons. And now, with that, so I have told you how do we basically gonna do this. But there is a way of interpreting the X-rays, the signal in the X-ray pulsar light curve. So this is how a particular X-ray counts on the detector looks like. So what we propose is that you should look for X-ray photon counts at 3 sigma level for 3 consecutive time beams. That would be a detection. And on top of that, we also ask for achromaticity, because in geometric optics regime, the microlensing is achromatic. So you have to basically know about what is the mass involved. So how do we test it? So basically, what you do is you plot the light curve, and you split into 2 different multiple energy windows. So if you split it in a different window, we can see there is no signature as such. So this is simply not microlensing. It could be some X-ray flares or bursts, or it could be even atmospheric electrons that are interacting with the detector components. Okay, so now, so this is the final thing. After, so if we find any signal, that would be a great thing. If we don't, then we can put constraints. So this is the, after all, microlensing is the counting experiment. So this particular expression basically gives you the differential lensing rate. That depends on the local dark matter density, because we have dark matter that is circling around the galaxy, and here this formula assumes that dark matter halo is virialized, meaning you have a system that is in equilibrium. So we take equilibrium distribution, that is Maxwell-Boltzmann. That's why you are seeing this exponential in the expression. And so using this expression, you can estimate what is the lensing rate, and from that you can count how many microlensing event you will see. So using this formula, you can basically try to constrain what is the fraction of primordial black hole as a function of mass. So that's where that will lead you to the final plot. So here you can see that, so all of this region has been ruled out, which is shaded. So here you can't find any primordial black hole. What we propose is that these telescopes are sensitive to detect primordial black hole in this particular region. Detect them or even exclude them. So NICER can do this job in just 2 months of exposure, and Stobax can do better and can probe even lower mass primordial black hole, because it works in higher energies, like it goes till 30 keV, and it can do much better job in just 1 month of exposure. And our XMU telescope can even go and probe the black hole in this particular region. And this is interesting because recently there was a paper by Dwali who proposed that primordial black hole could be evaporating at even smaller rates than what Hawking predicted, due to memory burden effect. And so if black hole exists in this particular region, then this kind of telescope would even be testify if Hawking was right or not. Right, so these are the take homes. So the primordial black hole in the mass range 10 to the minus 16 to minus 11 solar mass may constitute all of the dark matter. And what we showed is that the wave optic microlensing of bright X-ray pulsar provide the most robust and immediately implementable opportunity to uncover the primordial black hole dark matter. And NICER telescope, that is ongoing mission by NASA, can probe this window near 10 to the minus 14 solar mass within just 2 months of exposure on X-ray pulsar SMC X1. And the evaporation limit around 10 to the minus 16 solar mass that can be probed with a minimal microlensing setup involving hard X-ray pulsars. Yeah, I'm open for questions.
Thank you, Manish. Such a nice talk and nice topic. So question for him.
Yeah, so what is determining which telescope to use? Why not use, let's say, XMM, NewStar, all these extra telescopes?
Right, so the XMM effective area is slightly below. If you see the effective area of XMM Newton and the NICER, for instance, the NICER does a great job because its effective area is higher than XM Newton, I think. So the things that determines what telescope to use is mostly the effective area and what energy range it works in. Like if you are, for instance, observing SMC X1 pulsar, that the ACD of this pulsar mostly peaks in 2 to say tens of keV, and NICER also works in that particular range. So you have a convolution of effective area. So in this particular formula, you have a convolution of effective area and the ACD of the pulsar. So you get even higher magnification for that case. So if I show you the, oops. Yeah, right. Are these contours visible from back? Okay. So this W parameter you are seeing here, sorry, I think it won't describe that much better. So maybe I'll go to this plot. So for instance, you can see that this is NICER telescope and this is different telescope, Stobax. So this works in, this goes to 30 keV and this goes till 12 keV. You can see for same impact parameter, this telescope is seeing a magnification of 1.5 and this telescope is seeing a magnification of 2.55. So different telescopes, same source, but you are getting different magnifications due to effective area and the energies they work in.
Yes.
So I have two questions. So if there is a PBH merger that is happening in between, so will there be any distinct signature in the microlensing? That's one question. And for PBH spin,
Okay.
so if there is a PBH spin, so does this microlensing things have any distinct signature?
So for spin, I don't think so, because after all, it's a point lens. For a spin, you can't, if it is a PBH with a spin or not, you will see same signal. But for merger, you will see different signal because it is a double lens system. So you have to construct your lensing potential accordingly, and you can compute how much magnification you will see. With it, you will see in the light curve, you will see different features in the data. Like if you plot the light curve, you will see distinct signature. Yeah.
Okay, thanks.
If not, let us thank Manish and the other speakers of this session.